Moment.
Disculpen, parece ser que el ponente se le cayó la conexión. En breve retomaremos la conferencia.
Okay, I'm sorry. Can you now see me? Can you hear me? I accidentally left the meeting.
Don't worry. Yeah, we can hear you perfectly.
And now
Okay.
click here, continue. And then share the screen.
Where, I want to go here. And that is the screen I wish to share. And I'm not sure that I'm sharing it yet.
Here.
Here. I'm having trouble finding the screen I want to share.
This one.
Don't worry.
Okay, I believe screen 2.
And then
This one.
share. Screen
Okay, so hopefully now you're seeing my screen with the title page.
Yeah, we can see it. Perfect.
Okay, my apologies for the delay. So thank you very much, Gerardo, and it is a pleasure to be addressing the Venezuelan society. I only regret that we have to do this virtually. Obviously, I'm not good at that. And secondly, I would much rather be in Venezuela enjoying cachapas and papajan with all of you and seeing you face to face. Nonetheless, let me proceed with the presentation virtually. And I want to talk about some of the changes we've seen in land seismic acquisition over the past 2 decades. And okay, so I lifted this picture off of your web page, and it occurred to me looking through the group of people in this picture. Talking about seismic 20 years ago may precede some of your professional careers. In fact, it may precede some of your lives. I don't know. But I'm an old guy, and I'm hoping there's enough older people in your society that we can go back 20 years and you'll know what I'm talking about. So let's start talking a little bit about instrumentation and what we had about 20 years ago versus where we are now. So certainly 20 years ago, the majority of seismic was recorded with cabled recording systems. And at that time, there were primarily 2 systems that dominated the world. The Sercel 428 was commonly used at that time. Innova had the Aries, or what they now call the G3i. But what these had in common were they were cabled recording systems. All the geophones and recording system were linked by wire. Okay, so cabled systems have this in common. A lot of cables, a lot of wire that had to be deployed on the ground to bring the information from the geophones into a central recording device. Lots of wire has to connect to lots of boxes. That means we have lots of connectors, and that had been a problem in seismic for many years. Now, around this time, around 2000, a few autonomous nodal systems began to emerge. They were a little bulky at first, a little complex. We had things like the Geospace GSX system. Basically, it's a box or a little mini recorder sitting out in the station, servicing anywhere from 1 to 6 sets of geophones. Excuse me, operated by a battery and sitting there collecting data autonomously. Okay, We had the Sercel Unite. We had a couple of others at the time, the Fairfield system, the Innova Hawk. John Giles had a mesh network wireless system. Several things were evolving, but you'll notice all of these are a little bit bulky, a little bit large, and they were new to us. We were still learning. What's evolved since then is a whole series of very small self-contained units, and we have a large variety of them available. I'm not going to go into any detail about any one of them, but we have things like the Smart Solo has been around a number of years. The Innova or the Innosize Quantum is getting quite popular. Sercel has come out with a new one they call the Wing. We have the New Size. We've got the Stride. Hopefully, many of you have heard of these systems. Hopefully, some of you have had a chance to use them. But what they all have in common now are these nodes are getting very, very small, very portable, long battery life, and huge amounts of data available to be stored over a long period of time. Okay, what you have noticed is we've gone from 2 significant vendors to maybe a dozen different vendors of these systems now. And I think that's probably going to continue for a while before we settle down and say, okay, here's 1 or 2 of the best systems. And the reason it's going to continue is as soon as we abandon cables, basically anybody with access to a hardware store could find the components they need to build a recording system. And so there's been a huge influx of new ideas and new systems. That's kind of what's happened. Okay, so we've gone from cabled systems, and they're not gone. We still have many, many cabled systems around. They're good, and they have some advantages over the nodes. The nodes have some advantages over the cabled. So let's see what those are. Okay, the big one for cabled systems, the big advantage that most people see is we get a full set of data in real time every time we take a source point. Okay, so we get the feedback of all our real data. And along with that, of course, we can retrieve our full system status at any time. The big disadvantages of cabled systems, they were expensive. They remain about anywhere from $1,000 to $2,000 US dollars per channel. They're bulky, they're heavy to deploy. You require larger crews, and you're asking those crews to move bigger equipment, and they're more vulnerable to injury. Okay, a huge one was because everything was connected by cables. We had a lot of connectors, and cables and connectors fail frequently. So it was very common as you start a seismic program each morning, it's very common to spend several hours just troubleshooting your spread and fixing these problems. Okay, the nodal systems, of course, they have a big advantage in that they're quite low cost. Some of the systems are getting down to just a couple of $100 per channel. They are very light and easy to deploy, and you need a smaller crew size to deploy many more channels. There's no cables linking receiver stations, so we have more flexibility in where we can put the receiver stations. Much higher productivity, partly because they're so light and easy to deploy, and also because there's almost no downtime as you start up recording each day. Okay, I'm sorry, excuse me. Now another advantage of the nodal system is that we're no longer limited by cables to transmit our data through telemetry networks back to a central recorder. These telemetry networks were becoming limiting in terms of the total number of channels that could be transmitted back to a recorder. We no longer have that limitation. So effectively, with autonomous nodes, we have no limit on the number of channels we could place in the field. The big disadvantage is that we get no data return in most systems, or limited data from some systems. Many of the systems now, we can retrieve some level of status for each of the stations, which gives us encouragement that the electronics are working as they should. And the other big disadvantage is the high potential for theft. Now, we had that with cabled systems. We often had batteries get stolen from our spread. Sometimes the wire would go missing. Sometimes the boxes would and would be held for ransom. But what what concerns us more now is that not only do we stand to lose the asset due to the theft, but we lose the data. The data is sitting in those boxes until we download and harvest the data. So, that is a concern, and it's more concern in some areas than others, obviously. Okay, so we've kind of talked about the systems. What about the idea of using these point receivers as opposed to what we do more often with cabled systems is we use a small array of geophones distributed along our line. So let's just take a very quick look at what that entails or how it impacts us. In this picture, I'm trying to show a graph of a typical reflection signal, a typical reflection hyperbola arriving at the surface and how it might be measured in terms of its apparent wavelength across the surface. And I've got a wave number scale for those who are comfortable with that, or below here, a wavelength scale, which is just the inverse of wave number, of course. And what we see for most reflection signals is at near offsets, we tend to have very long apparent wavelengths because the emerging wave field is parallel to the surface. As we move to further offsets, we see normal move out and we start to see shorter apparent wavelengths, and low frequencies and near offsets dominate our long wavelengths, and some short wavelengths come from the very high frequencies and very far offsets. So this is kind of the distribution of signal in the wavelength domain. Most signals, once you're down at reflectors down around 800 milliseconds a second or deeper, it's rare to see useful wavelengths, anything shorter than about 80 meters on most reflectors. Of course, this has to be evaluated prospect by prospect, but I'm going to assume that typically we have reflection signals of interest down to about 80 meters wavelength, apparent wavelength. And according to Nyquist, we must sample that 2 times per cycle, which means we should be using a receiver interval, perhaps of 40 meters, if we want to measure all our signal correctly. What happens if we have a longer receiver interval with 80 meter desirable wavelengths? Well, then we're experiencing what's known as aliasing. The red curve is the true wavelengths of signal that we would like to record. What happens is any portion of that signal that is at shorter wavelengths than our Nyquist, that will be aliased. Okay, it means it does not mean that we don't record it. Unfortunately, what it does mean is that we record it badly. We don't record it as short wavelengths. We record it as longer wavelengths, which then contaminate our true signal in those same wavelengths. So this is just showing how aliasing, the short wavelengths that are not measured, wrap around and contaminate our desired signal in the signal band is what I'll call it. Okay, so we must use an appropriate receiver interval that is less than or equal to 1/2 of our shortest wavelength of signal we wish to acquire. So that's measuring signal, but what about noise? And I am going to talk in particular about broadband noise that contains all wavelengths, kind of uniformly. Wind noise is a good example of this, but it's not our biggest problem. Chaotically scattered source generated noise. A lot of people have been talking about that recently. We've been talking about it for many years. It has a characteristic that it tends to look random in the wave number domain. In other words, it contains all wave numbers. So certain modes of noise are broadband in wavelength. Okay, and that's represented by this blue curve on this slide. Our signal is still here as the red curve. And if we measure the signal correctly with a 40 meter wavelength, what will we be doing with the noise? Okay, well, any part of the noise, which is at shorter wavelengths than the Nyquist, or 40 meter receiver interval Nyquist, all of that will alias and wrap back into the desired signal spectrum and contaminate. So little segments, each of these segments, kind of between the vertical lines in this graph, each segment will wrap back into the desired signal area, and the result will be a very high level of noise compared to signal in our recorded data. And that's just unacceptable. That's when we see terrible data and have trouble recovering any useful signal. Okay. Now, one way to mitigate this would be to use a smaller receiver interval, change our Nyquist, go down to a 20-meter receiver interval. Our Nyquist would then be at 40 meters. We would have less data to alias, and we have more space in the passband to distribute that aliased signal. So the signal to noise ratio improves. We reduce the level of noise. And if we further decrease our receiver interval, now 13 meters, we can get to an almost one-to-one signal to noise ratio in this example. So reducing the receiver interval with point receivers allows us to reduce the amount of aliased broadband noise. That's an important thing to remember. There is another option that we've used in the past, and that is if we use an array of geophones, perhaps 6 geophones uniformly distributed over a 40-meter recording interval. And those 6 geophones would then be separated by about 6 2/3 meters. This dashed line would be the Nyquist for that spatial sampling. Now, 2 things happen when we use an array of geophones. We're going to sum those geophones together electronically and produce 1 recorded trace every 40 meters. So the 2 things that happen is the formation of that sum creates a spatial filter, a wave number filter indicated here by the green curve. And if you take our broadband noise, the heavy blue line, and you filter it with this green function, what's left is this lighter blue curve down near the bottom of the graph. So that's our noise as filtered by the geophone array. The second thing that happens, of course, we sum those elements together. We produce 1 recorded trace every 40 meters. So now our Nyquist moves to a 40-meter sample. And all of the data that was in the light blue curve, anything to the right of the new Nyquist, that will alias. But we're not aliasing the heavy blue signal, our noise, we're aliasing a reduced version of that. And this is what that looks like. So here's the same level of noise as managed by a geophone array prior to producing a recorded trace every 40 meters. Compare that to what we get if we have just a single element every 40 meters. So there is a danger in using single point receivers if you have an area where there's a lot of chaotic scattered noise, broadband noise. Okay. If the noise itself is very weak, then we're not too worried about this. Okay, the noise plus signal is very small. When it aliases, it is still very small. It's just not of a concern to us. So there are many areas where we can use single sensors at large intervals, and it's just not going to hurt us. Okay. However, if you do have short wavelength noise modes, if they're going to be significant, then you should consider using a geophone array to subsample your large receiver interval. Or if you're going to use point receivers, you should reduce your receiver interval, perhaps by a factor of up to 3. Okay. Now I'm going to go quickly through this part. I wanted to talk a bit more about some of the advances in vibroseis over the past 20 years, but there's another part of the talk I'd rather spend more time on. So I'm not going to dwell too much on vibroseis here. Basically, the big machines have gotten bigger over the last 20 years. We've gone from 50,000, 60,000 pound machines. We're now in 80, 90,000 pound machines. What that means is that if we want, we can operate those machines at a much lower drive level, still get the same net signal into the ground as we did with the lighter machines, but we'll have much less distortion and we'll have the ability to sweep into lower frequencies without cavitating our pumps. Smaller vibes, well, they haven't gotten smaller, but they've stayed about the same footprint, but they've gotten much more robust, stronger, more force. They're becoming a very, very useful tool. Okay. But one of the things that has changed over the years is, over the past 20 years, is a lot of people wanting to get low frequencies out of their vibrators. And as you probably know, it's difficult for a machine to shake into low frequencies because of the fluid demand in the strong low frequencies and the potential of cavitating pumps. But there are a number of low frequency sweeps that have been used quite a bit. Western's maximum displacement sweep, CGG's emphasize. Basically, the idea is we're going to spend a little bit longer putting the signal in at a very low amplitude. So we'll put in the low frequencies over an extended period of time, but at a weak amplitude. And then we go to full drive level and go through our normal sweep rate. So this is one of the things that has changed. I won't get into detail with it here, but that's more and more what we're seeing being done. Now we do, another thing that has changed is we often used to do a lot of sweeps. We do like 8-second sweeps or 12-second sweeps. And we have learned that the signal to noise ratio of a single sweep versus, for example, the signal to noise ratio of 25 sweeps. This is a real data example from Qatar. It's typical of what we've seen in over 300 vibrator tests. A lot of sweeps does not normally change your signal to noise ratio significantly. And I'll explain why in a couple of minutes, but I just wanted to keep this slide for reference in an upcoming slide, okay? So what we have learned is that we don't need a lot of sweeps per VP. We're better to spend our time doing more VPs, smaller, a higher density of source points. If low frequencies are desired, we may need custom sweeps in order not to damage the vibrators. And some of you may be familiar with a broad variety of simultaneous sweeping methods where we get higher productivity, but by and large, those are very well suited to North Africa and the Middle East, where we have large open areas with no cultural restrictions and multiple fleets of vibrators can move around easily. Sorry, that's all I'm going to do in this talk about vibrators. I want to spend some time talking about how we've changed the way we think about 3Ds and how we design them. So just a quick overview from 20 years ago. Here's a simple orthogonal 3D with north-south source points and east-west receiver points. And in green, you see perhaps a bin grid. What we used to mean by bins was by default, they were 1/2 our source interval by 1/2 our receiver interval. Okay, when we collect record traces in a 3D, here I'm showing one source point. Of course, with that source point, we'll record many receivers. Here I'm showing one of the receivers we record. And we can talk about a few statistics. We can talk about the source location, the receiver location, the distance between them that we call offset, the direction from the source to receiver that we call azimuth. We can talk about the midpoint, which is the geographical average of the X and Y coordinates, okay? And the idea is in our minds, we assume that the trace recorded by that source receiver pair is somehow imaging the subsurface associated with that bin near the midpoint, okay? Here's 3 traces, a mid and far offset have now been included. We have different offsets, we have different source receiver azimuths. These are all important statistics. When we finish our survey, if we've done it well, we will have a collection of many traces, all of whom have midpoints that fall inside the same bin, okay? So this is the significance of a bin, is we're going to collect traces to stack based on which traces have midpoints within a bin. The number of traces we have, of course, is called the fold, and that's about all I want to say about fold. It's going to be, in my mind, one of the least important statistics in a 3D. We can talk within each bin, we can graph how are those traces distributed in source receiver offset. Okay, and that becomes a fairly important statistic. And you will notice a certain sparsity in the near offsets and a higher redundancy in the farther offsets. And that's very simple. The geometry of a 3D is shown here. A 2D, the horizontal line through the middle, if we have a shot point reaching out to our geophones spread out to our maximum offset, we will find that 1/3 of those geophones are sampling near offsets, 1/3 are sampling mids, and 1/3 are sampling far offsets. When we do a 3D and we listen to geophones distributed all across the surface, we find that our near offsets account for only 1/9 of the total traces. The mid offsets are 3/9 or 1/3, and the far offsets are more than 50% of our traces. They're 5/9 of all traces recorded are far offsets, assuming that we're recording with a wide aperture patch. Okay. Another statistic we've looked at used to be called the spider plot. Within each bin, perhaps we have 20 traces. We will graph the statistics of each trace as a vector. The length of the vector would be the source receiver offset, and the direction from the center outwards represents the source receiver azimuth. So again, we're looking at trying to create a variety of statistics. Okay. Oh boy, where am I? I'm having trouble. There we go. All right, if we look at just the tips of the spider legs there and just graph the tips, we get a polar plot of offset versus azimuth. So each dot here, it does not represent the location of the midpoints. All of these traces had midpoints within that bin. What we're looking at now is a polar plot of the source receiver offset versus azimuth. Okay, and what we want is a nice uniform distribution from near offsets where the plus sign is to far offsets where the outer rim of the circle is. We want lots of traces, yes, we want fold, but we want that fold well distributed in this domain, the offset azimuth domain. So this would represent a fairly good 20-fold program. If our distribution within a bin looked like this, where all 20 traces are clustered in one area, well, that means we're basically using the same source point or same receiver point. We're generating the same offsets and azimuths. This, by the way, is why a 25 sweep vertical stack doesn't affect our data very much. It's only going to attenuate noise that is unrelated to our source and is random and more or less Gaussian distributed. Okay, we get much better noise attenuation and much better averages of signal if we can have a great variety of different source locations, receiver locations. That's what it takes to give us a good distribution in the offset azimuth domain, okay? That's what's more important. Fold, in my opinion, it's you get pretty colors, makes a little pretty picture that maybe you can hang it on your wall and brighten up your office, but that's about the greatest use of a fold plot. Beyond that, it is not a useful measure of survey quality. Okay. We think it's important to have a lot of traces, trace density or fold, but it's very important that those traces be statistically diverse in the way they've been measured. Okay, a quick reminder, any kind of CDP gather needs to be move out corrected before we stack our data, and we mute the poor quality data. And what that means is that shallow reflections are only useful from 0 to a near offset. Medium reflections, I can use more offsets. Deep reflections, I can use everything out to very far offsets. So we talk about our maximum usable offset. It's a target dependent value. It's closely related, we found, to depth, target depth. And in general, it's usually somewhere around 1.2 times your depth to your target is your maximum usable offset. Okay. When we record seismic data, if we record a large patch, what we call a wide aperture patch, if our usable offsets exceed that patch in all directions, then every trace we record will be useful at our target. If our maximum usable offset falls within the recorded patch, there will be some traces that we record that are no longer useful for that particular target. So we can talk about offset limited fold. Okay, nominal fold is something I don't like quoting. It's basically your total surface patch area divided by 4, puts it in the subsurface, divided by your line spacings, what we call our box area, the area between 2 adjacent source lines and 2 adjacent receiver lines. That's our fold in natural bins, and it's called nominal fold. Okay, if you're comparing surveys that have different bin sizes, it's often useful to convert that to trace density. You get a value in a certain number of traces per square kilometer, and you get that by dividing your fold by your bin size, normalizing it by the bin size. More often, it's more useful to talk about offset limited fold, okay? And if we recognize that X max is often a function of depth, in fact, in this example, I'll say X max is 1.128 times depth, then this equation boils down to the fold we get is basically our depth of target squared divided by our box size. Okay. Now using that equation, let me reverse it so that we're talking about the box size must be less than or equal to the depth of our target squared divided by the desired fold you want. This is the designer's equation for a 3D. That's the largest source receiver line spacing I can use and still achieve the fold I want at my target depth. Okay, that's the largest it can be. It's not what I should do necessarily in a design. The smallest my line spacings can be is if my source line spacing is equal to 1 receiver interval and my receiver line spacing is equal to 1 source interval. So normally in this top equation, we will round our source line spacing so that it's some kind of integer multiple of the receiver interval. So maybe I'll pick a source line spacing that has 7 receivers between line spacings, and I'll pick a receiver line spacing that has 5 sources between receiver lines. Okay, the smallest we can go is 1 and 1. Okay, what should we do? I have a target depth, I have a desired fold. It tells me what the largest box size I should be, tells me what my smallest box size should be, and where I need to go often depends on the extent and type of noise that we have. So if you've never seen a survey where the line spacings equal your source and receiver intervals, this is what it looks like. We call it a full wave field sampled 3D. And yeah, as you can imagine, it's very expensive. But it has been done. We have done ourselves something like 6 of these, and I'm aware of about 3 others in the world that have been done. Normally, we can't afford that. So we start saying, hey, would it be okay if I don't record all those north-south receiver lines? Can I just record every 4th one? Can I just record every 6th source line? Would that be okay? And that would look like this. So this is a more normal orthogonal, and we often talk about the sparsity. This is 4 sources between receiver lines, 6 receivers between source lines. We call it a 4x6 sparsity. So that's where we often go with our 3Ds. Okay, excuse me. Now, here's an Argentine example, okay, where I recorded in 1997. Our client had very good data using a 5x7 sparsity. He had very poor data in a few areas due to some basaltic sills, some intrusives near the surface. Okay, yeah, we did some modeling for him, and we took a CDP gather from a super gather from the very good data area, and we showed him what would happen if he built a 5x7, his original survey design, versus tightening up the grid to a 4x5 or a 3x4. And you can see there's a big impact in the cost, okay? But you see very little improvement in the data quality here, all right? We also did the same simulation in using a super gather from the very noisy area, and showed him that in his noisy area, if he does not go to the small grid, he's never going to get good reflection data, okay? So we did convince him to, he convinced his manager to go out and reshoot a 3D. Unfortunately, he could not convince his manager to go all the way to our recommended parameters. He went to the middle of the road parameters. On the left is his original processing of the original 3D. In the middle was more recent processing of the original 3D. And on the right is the more recent processing of the reacquired 3D using just the 4x5 sparsity. We really wish he had gone to the full extreme of the tight grid, but even with this, you can see that he did start to get a reliable interpretation near his target level down below, even under the bad data area. So certainly trace density and fold, yes, they're important, provided you maintain a good offset distribution and azimuth distribution. So I'm going to work through 2 examples here that are kind of very different, but also very similar. They're both designed supposedly for a target at 3,000 meters, where we'd expect maximum usable offsets of perhaps 3,600 meters. We're going to build 2 surveys, 100 square kilometers, and one on the left is going to use 40-meter source and receiver intervals, generating natural bins of 20 by 20. The line spacings will be 200 by 240. In the right hand, we're going to go to a slightly larger source receiver interval, 48 meters, and the line spacings are going to be considerably larger. So this one is a 5 by 6 sparsity. This one is a 9 by 12 sparsity. And look at the difference in the number of receivers and sources required. So which one do you think is going to make the better data? And be prepared to be wrong. Okay, let's move on. How are we going to shoot these two surveys? Well, in the old days, we had a tendency to shoot very asymmetric patches. This is an 8 by 144 patch. Today, we try to shoot wide aperture, wide azimuth patches. This is a 16 by 144. It requires twice the number of channels, but it's covering much more of the usable offsets. Around this shot, in each case, I've drawn a black circle, which is the 3,600 meter radius. All receivers within the black circle could produce useful data. In the right side, we're recording most of those. On the left side, we have a high density of traces, but we're not recording all the offsets and azimuths that are available. The other difference in here, the right side is triple staggered. I hope you know what that means these days. We've been doing them for, well, since the mid-80s. But what it does mean is around each line intersection, our lines are offset differently in sets of 3. So notice that at the center of this one, the nearest receiver and source around the intersection is a half an interval away from the intersection. But the receivers on the next intersection, this is 1/6 of an interval to the first receiver. This is 5/6 of an interval to the first receiver. And we do a similar staggering in the source lines. It doesn't add any source points or any receivers. It just, well, I'll show you what it does. It makes a difference. Okay, if we look at just the fold, the offset limited fold, limiting from 0 to 3,600 meters, on the left, because our patch is totally contained within the usable offsets, we get a full uniform fold of 48. All our traces count. On the right side, we recorded some traces that were outside the 3,600 meter usable offset. So we actually are down around 40 to 45 fold here. Okay. The trace density, I'm going to skip past this. It's not important. I'm going to zoom into the center of one of these surveys, and we're just looking at the bin level here. Each square is one natural bin. On the left, it's 20 meters by 20 meters. And the dot in the center represents the location of the midpoints of the traces in that bin that contribute to that bin. So we have 48 fold, we have 48 traces, all of whom have the same midpoint at the center of this bin. And 20 meters away, we have another 48 traces, all of whom share the same midpoint. And 20 meters away, we have another 48 traces, all clustered at the same midpoint. On the right, the triple stagger introduces a planned midpoint scatter. So now we have 24 by 24 meter bins. We still have around 45 fold per bin, but instead of having 45 fold every 24 meters, we actually have about 5 fold every 8 meters. So every 8 by 8 meters, we have a collection of 5 traces. That's called midpoint scatter. And this only gets enhanced further when you implement a program in the field and we get natural perturbation from implementation. Okay, we talked about the offset azimuth plots. So in each bin, I've now made a graphical plot, a polar plot of offset versus azimuth. The outer ring represents our 3,600 meter offsets. The middle ring represents offsets of 2,400 meters, and the inside ring is 1,200 meters. And you notice because of the very asymmetric patch that the survey on the left produces a very asymmetric sampling of azimuths and offsets. We have pretty good sampling in the inline direction, but in the crossline direction, we only are recording near offsets, no mids and fars. With the wide aperture patch, we are getting 45 traces uniformly distributed across all usable offsets and azimuths. Okay, so how does that affect our migrations? So here's an example from the Middle Magdalena Basin in Colombia. This is out of a 3D volume. This is an unmigrated inline slice. And this is the migrated inline slice. The migrations are so important, and that's one of the huge benefits of 3D is the 3D migration that brings all elements into focus in a migrated volume. Okay, so how does migration work? Well, here's the unmigrated section. We consider one trace out of this migrated section, and we apply a migration impulse response to it. We take that trace and we smear out its reflections to all possible locations they may have come from. Okay, so the migration operator can position data in a flat horizon, or it can move it outwards and upwards into steep dips. And these operators for each trace then interact, and where real geologic dips occur, the operators interact constructively, and we get a migrated section. Okay, so if we want to migrate steep dips, we must have an operator that produces reliably the steep dip components. Here's the operator, okay, and I'm going to zoom in on a portion of it. Here we're looking at an open filter. Notice that near the near offsets of the migration operator, we have relatively high frequencies. As we go further out, these look a little lower frequency. And there's a reason for that. If we look only at the high frequencies of that operator, 40 to 120 hertz, what we notice is that the operator is well defined in the near offsets. As we go to the far offsets, we're now experiencing aliasing. That's spatial aliasing of the migration operator, because we included some frequency components that we should not have included. That's alias data, and in a migration operator, if all the operators alias, it's possible that the operators will interact constructively and produce little events where they don't really belong. And that has happened in many places, and it has resulted in several very expensive dry holes. We must mute that migration operator, okay? So after muting, after the anti-alias application of a filter, this is what the high frequency components look like for a operator sampled every 21 meters, and here for 14 meters. What I want to show is the same operator. The anti-alias filter depends on the trace spacing, the sampling in the offset domain. And a smaller sampling allows more of the operator to exist at higher frequencies and steeper dips. Okay, so now let's take a look at our two surveys. I'm going to look at something, I want to migrate a point out at the center where these black dots are. And in order to produce that migrated trace, I need to look at all the traces around me with my migration operator. So here I'm looking outwards about 1,800 meters, actually, out to 1,800 meter offsets. So both of these surveys have a migration operator that is going to examine all of the traces, if you want, the pre-stack traces in a pre-stack migration. We're going to examine all the pre-stack traces in this area around each survey. And if we graph an offset versus azimuth plot of the collection of traces that we're going to migrate, this is what we have for the two surveys. Because of the very limited patch, recording patch used on the left side, these are the traces that we're going to be migrating. And we're going to miss out on the very far offsets where the steepest dips are. Cross-line component is not going to migrate steep dips very well at all. And on the right side, we have a migration operator that is well sampled in all azimuths. We're going to get a much better, more powerful 3D migration. And if we look in detail at the center of these, this is the points that we have in the offset azimuth domain. The points are separated by our receiver interval, which is 40 meters because of the midpoint focusing. When we look at the right side, we had a 48 meter receiver interval, but we used triple stagger, and that produces statistics every 16 meters. We're much better sampled, we're more finely sampled, we're going to be able to migrate steeper dips and higher frequencies because of the midpoint scatter. Okay. Okay, so what's the best survey? I wouldn't shoot either one of these today. I wouldn't. But certainly I could shoot with much smaller number of sources and receivers, and I could get better results than the survey on the left. What if I was doing it today? I would actually make a much more dense survey. I would try to make this more like 100-fold instead of 48, but I would definitely do wide aperture. Okay, what's so important in 3D is how we migrate the data. Okay, now I'm near the end of my time. I'm going to beg 5 minutes extra. I had told Gabrielle that I would probably need 50 minutes for this. Okay, but let me just show you an example. This is a real example, but unfortunately I cannot show you. We don't have permission to show the actual migrated data. But the concept here is we shot a survey that had an inline azimuth, kind of shown by the diagonal through these bins. This is a zoom in to the middle of the survey, and it was shot with a 42-meter receiver interval and a 48-meter source interval. So the natural bins are 24 by 21. And what you're looking at is several bins with a plot of the midpoint scatter. Okay, so it's a fairly high fold. You can see lots of traces in each bin. Now, what I want you to see visually is watch the pattern of dots. I'm going to take exactly the same survey. Okay, the midpoints have been defined when we acquired the data. So those midpoints stay the same in all of these pictures. But what I'm changing is the bin grid I superimpose on this. So when we have lots of midpoint scatter, I don't have to use a bin that is a half a receiver interval by a half a source interval. The bin doesn't have to align with my receiver azimuths. I can arbitrarily change my bin grid, superimpose it on the midpoint scatter, and I can gather that data in 21 by 24 meter bins. I can make them square bins, which is better for a symmetric migration operator. I can make 21 by 21, or if I think I can get more resolution in my stacked data by going to 14 by 14 meter bins, I can do that. The bin grid can be decided at the time of migrating your data. It does not have to be fixed by your source and receiver interval. And that is the beauty of midpoint scatter. And not only that, but in this survey, we found that the original orientation was defined to be perpendicular to the faulting that was mapped by 2D data. Once we interpreted the 3D, we found that the faults really had a slightly different orientation. And if you want to look at your inlines and have them perpendicular to your fault, you may want to rotate your bin grid and produce migrated traces at a different azimuth. And you can do that again using exactly the same set of midpoints. How you organize that bin is entirely up to you. And the idea will be to choose the right size of bin and the right orientation of bin to optimize your bandwidth after migration and your ability to image the faults. This has been done. We've been doing this for a lot of years. These are some very old examples, more than 20 years ago. This is the same survey acquired and processed in natural bins on the left, and on the right, we have sub-binned down to a considerably smaller bin size. And look at the increase in resolution of that little channel. Okay? Or another example, a deeper example from Devonian Reef in northern Alberta. This is a survey that was originally acquired with a natural bin of 40 meters. Okay. And there's a reef right in here with a reef rim that stops somewhere in here. And a well was drilled. Unfortunately, it missed the reef rim. But when that data was reprocessed to 15 meters, we much more clearly see the reef, the lagoonal facies, the reef rim, and the off reef. Much better imaging. Same data, just reprocessed, rebinned, and migrated using an output migration interval of 15 meters. Okay. Well, this is what we do. We try to design a good survey with the right bin size. We will process it through to a migrated stack, post-stack migrated. From that, we try to find the most complicated area in our data set. And we take a small volume of our data around that complicated area, and we test by rebinning it and pre-stack migrating to smaller bins, reorienting the bins if necessary, and try to find at what point can we gain a bit of resolution. And very often, if we've got the right bin size to begin with, you won't see any significant changes. But this is a worthwhile test. And sometimes you will see significant improvements in your data when you do rebin it. So just before I leave you, I want to open your mind a little bit more to some different kinds of 3D designs. This is an urban area. This is the city of Los Angeles, where we have shot many 3Ds. One in particular, this is the type of area we're in with residential and commercial activity in a city. This is a large 3D we shot with a carpet receiver grid. You'll notice there are no receiver lines. It's just a uniform distribution of receivers every 100 meters by 100 meters. The source lines, well, we pretty much had to run vibrators on the roads, so we were limited where we could put the vibrators. In detail, you can see the vibrators working. The red squares are all on roads. The blues, the receivers, those are put into people's yards. They were Fairfield nodes buried just below the surface. Okay, and that survey gave us a broad variety of a huge midpoint scatter that we were able to collect in 25 by 25 meter bins and get a fairly uniform looking fold. And now in processing advances, of course, we would take this and apply a 5-component trace reconstruction, and that would really smooth out the statistics and provide an even better migration. This data, when interpreted, actually changed the perception of where the faults were, the major faults running through Los Angeles. One more type of design I want to show you that I think is very worthwhile knowing about. It just takes a couple of minutes. We call it the flared grid design. It's intended for areas. This happens to be a Mongolian example. It's an area where your target, when you map it, has a significant difference in depth from 3,000 meters on one side of the program to 500 meters on the other. So if your line spacing is supposed to be determined by the depth of your target, well, I suppose that when the depth is large, you need a large line spacing. Where the depth is shallow, perhaps you need a denser line spacing to properly image this. So this is a first order surface determined for that structure. And what we see is there's a tendency of the structure to go from 1,000 meters to 2,000 to 2,500. The black circles around here are the usable offsets, which are slightly larger than the depth. Okay, the usable offset at the deep end here is 2,875 meters. So we really have more usable offsets that we want to record as we go deeper, more usable offsets available to make a usable, a reasonable fold in our 3D. So the flared grid design, if you've never seen it, it looks like this. The source lines are parallel to each other, but the spacing between the lines increases as we go deeper. The receiver lines are not parallel to each other. They flare outwards from a tight spacing in the shallow area to a wide spacing in the deep area. And what the flaring of the receiver lines does is it means I can, well, let me explain these numbers. No, I won't, not just yet. What this does is it says when I have a 16 line patch, in the shallow area, my 16 lines are fairly close together and they're suitable for imaging the available offsets at my target level in the shallow part. As I go deeper, my 16 lines get further apart and they are still suitable for measuring the fold in those usable offsets. So as I go deeper, my patch naturally gets wider and we're still doing wide aperture recording based on the depth and available offsets as the target increases in depth. Okay, I've probably gone a little over my time, and I think Gerardo has been very generous, letting me keep on talking. That's really all I've got to say. It's nowhere close to what I have to say. If you've ever been to one of my courses, you know that I can talk about this for 5 or 10 days and just keep going. But I hope I've given you a hint of the things that can be done with 3D design. Okay. And with that, Gerardo, I'm ready to embrace any questions that the group may have.
So you have to,
Okay, thank you, Mr. Cooper. So is there any question in the group? Okay, since none, I think that that's up for today. Thank you very much, Mr. Cooper, for being part of this conference. And well, that's all for today. Thank you all to all the audience. Gracias a todos los participantes en la conferencia. Y esperamos verlos el mes que viene con la siguiente conferencia mensual de la SOVG. Les estaremos informando. Thank you to all. I'm going to close the meeting.
Okay, muchas gracias.